How else can we think about the bonds present in methane if not by hybridization? Well, we need to go back to basics. What's involved? 1 carbon atom and 4 hydrogen atoms. First, let's think about the hydrogen atoms. Notice here they're positioned in a tetrahedral manner. All you have to do is put a carbon atom in the middle, form the bonds, and you have methane. That positioning is going to become key as we think further into the problem. Next, we consider a situation where 2 of the hydrogen atoms have electrons that are not in phase with the other 2 hydrogen atoms. Before we've depicted this as plus and minus, here the phase is indicated as a clear orbital being in phase with another clear orbital, and a grey orbital being in phase with another grey orbital. But clear and grey orbitals aren't in phase with each other. Next, we're going to think about just 2 of the hydrogen atoms. The other 2 atoms are there still, we can see they're marked as H, but they're not involved in the bonding that we're going to think about in that respect. Notice that left and right hydrogen atoms in this case are out of phase with each other. Lastly, we're still thinking about just 2 of the hydrogen atoms, but it's the other 2 this time. And again, forward and backward hydrogen atoms are out of phase with each other. That's the hydrogens. What about the carbon? Well, in the carbon's case, we know we're dealing with an s orbital and p orbital, p orbital, p orbital, where the p orbitals are orientated differently from each other, one in an x-axis, one in a y-axis, and one in a z-axis. Clearly, it's going to be important to describe spatial relationships between orbitals. And by doing this, we begin to understand how orbitals bond with orbitals. We have 4 orbitals on the left, 4 orbitals on the right, but what orbital bonds with what orbital? Well, let's go and think about 3D. Let's have a look at the molecule itself, methane. And what we're looking for are elements of symmetry. In this case, there are 2 elements of symmetry, and they're planes of symmetry. One is in the y-x plane, the other is in the y-z plane. And if we can imagine the plane cutting through the molecule, we can see it actually bisects or cuts through some of the atoms. Let's have a look at the y-x plane example first of all. Imagine putting your eye on the right-hand side and looking down the plane towards the left-hand side. What would you see? Well, the upper hydrogens are overlapping, one on top of the other. The lower hydrogens, one is on the right-hand side of the plane, the other is on the left-hand side of the plane. In fact, the 2 sides of the plane are mirror images of each other, and so we describe this as being symmetric. The YZ plane also has symmetry. So now we will consider all the orbitals with respect to y-x plane and y-z plane and evaluate the orbital as being symmetric. That's to say, having mirror images on either side of the plane, or asymmetric, where either side of the plane is not a mirror image of the other side. We're going to start by looking at carbon. Let's consider the s orbital of carbon. If we look at the s orbital of carbon in the y-x plane and look from right to left, we can see immediately that the left-hand side of the plane and the right-hand side of the plane are mirror images of each other, and thus this is symmetric. So we will mark this as S. If we look at the s orbital of carbon with respect to the y-z plane, we can also see that this is symmetric. So yx plane is symmetric, yz plane is also symmetric. So now we're going to go on from the s orbital to considering the different orientations of p orbital in the carbon atom. Firstly, we will think about the py orientated orbital. If we look at this from a yx plane point of view, we will see that either side of the plane is a mirror image of the other side, and so it's symmetric, S. Let's take a look at the YZ plane. Again, mirror images from either side of the plane, so it's symmetric, S. YX, symmetric, YZ, also symmetric. Let's now consider the PX orientated orbital. If we think about the YX plane, we will see that either side of the plane is a mirror image of the other side, and so it is symmetric. Now let's think about the YZ plane. This is a little more complex. So again, we're going to place our eye on the right-hand side and look from right to left and imagine what we would see. Well, what we can see is that on the left-hand side, the electron is out of phase with the right-hand side of the plane. This is not a mirror image, and so we describe it as asymmetric, or A. So YX plane, S for symmetric, YZ plane, A for asymmetric. Finally, let's have a look at the PZ orientated orbital. If we think about it in the YX plane, we can see by placing our eye on the right-hand side and looking from right to left, what is on either side of the plane? Well, it's electrons that are out of phase with respect to each other. The left-hand side of the plane, electrons are out of phase with the right-hand side of the plane. They are not mirror images of each other, and so they are asymmetric, or A. Finally, let's think about the YZ plane. When we do so, we can see that either side of that plane, the orbital is a mirror image of the other side of the plane. It's symmetric, so S. So YX plane, asymmetric, YZ plane, symmetric. What about the H4 composite? Remember, we're still looking for the same thing, whether one side of the plane is a mirror image of the other or not, as the case may be. So looking at H4, we're going to consider the YX axis, then the YZ axis. First, the YX axis. You'll notice that some of the hydrogens have been colored in red. This doesn't mean they're chemically different, and it doesn't mean their electrons are in different phase. We're only doing this so that you can locate the same spatial atom when we move between the YX axis and the YZ axis. Hopefully that's helpful. So if we place our eye on the right-hand side and look right to left, what do we see? Well, with the upper hydrogens in red, one lies on top of the other, so we're only going to see the front one there. They bisect the plane. With the lower hydrogens, the left-hand side has one hydrogen, and the right-hand side of the plane has the other hydrogen. Overall, one side of the plane is a mirror image of the other side of the plane. So here we have symmetry. When we look at the YZ plane, we see a similar but slightly different picture. We place our eye on the right-hand side looking from right to left. What we see is that the upper hydrogens are not bisected by the plane. One is on the left-hand side of the plane, and one is on the right-hand side of the plane. Again, they're colored in red. The lower hydrogens are bisected by the plane. Overall, one side of the plane is a mirror image of the other side of the plane, so again, it's symmetric. The YX plane is symmetric, and the YZ plane is symmetric. Now we're going to consider H4 star. In this case, some of the electrons are in phase, for example, the clear atom being in phase with the clear atom. And those electrons are out of phase with electrons in other hydrogen atoms. Those are marked, if you will, cloudy. Let's look at the y-x plane. When we do, we can see that both sides of the plane are mirror images of the other side, and so we have symmetry. If we look at the YZ plane, again, both sides of the plane are mirror images of the other side of the plane. It's symmetric. So the YX plane is symmetric and the YZ plane is symmetric. Next, we're going to consider just two of the hydrogen atoms. The other two are shown in grey, as if they were ghosts. Now, I'm fairly certain technically you can't have ghost hydrogen. However, the purpose here is to give you a sense of where their location is, but we are not thinking about their orbitals, nor are we going to involve them in any bonding. It's just the two orbitals that are marked in black that we're going to think about. So this is described as H2 star X. The star means we have anti-bonding present, and as you can see, the upper hydrogen on the left is marked as a clear orbital, and the upper hydrogen on the right is marked as a cloudy orbital. As we look through the y-x plane, the y-x plane bisects both atoms, and so either side of the plane is actually a mirror image of the other side, and it is symmetric. As we look at the same arrangement from the YZ plane, we attain a different answer. We place our eye on the right-hand side and look right to left, and imagine what we're seeing. To our left as we look at it, and to our right as we look at it. Well, here on our left-hand side we have a cloudy hydrogen orbital, and on our right-hand side we have a clear hydrogen orbital. So that's to say the two hydrogens have electrons that are out of phase with each other. So we are not having a case where one side of the plane is a mirror image of the other, so this is asymmetric. So the y-x plane is symmetric and the y-z plane is asymmetric. Finally, we will look at H2 star in the Z orientation. The X orientation was left to right as we looked at it through the y-x plane. The Z orientation is front and back as we look at it through the y-x plane. Again, we are showing the two other hydrogens as grey or ghost hydrogens. But really, we're thinking about them just to let you know where they are, but they're not part of the calculation. So, in the y-x plane, if we look from the right-hand side going from right to left, we will see that on the left-hand side we have a clear hydrogen orbital, and on the right-hand side we have a cloudy hydrogen orbital. The electrons of those hydrogens aren't in phase, and so we don't have a mirror image of one side of the plane with regard to the other side of the plane. This is asymmetric. What about the YZ axis? Again, the ghost hydrogens we can ignore. They're just there to let you know where the other hydrogens lie. If we look down the YZ axis, we bisect the two atoms, and so one side of the plane is a mirror image of the other side of the plane. So it's symmetric. Thus we have YX plane being asymmetric and YZ plane being symmetric. We've analysed the symmetric elements of methane and determined them to be the YX plane and the YZ plane. We've gone on to look at the orbitals and with respect to those planes, whether they are symmetric or asymmetric. Now, the question is, was that pure torture, or did it have some sort of point? And happily it did. Let's see what it is. Going back to the orbitals, we can now mark them as AS, SA, or SS. Now, an orbital on the left-hand side can only partner with an orbital on the right-hand side to create bonding orbitals and antibonding orbitals if they have the same sense of symmetry or asymmetry with respect to those planes. That's to say, only AS can partner with AS, only SA can partner with SA, and only SS can partner with SS. In some cases, that leads to some pretty simple conclusions. But in others, we need to think a little bit more deeply before concluding what the actual partnerships are going to be. So if we look on the left-hand side, there's only one AS. On the right-hand side, there's also only one AS. There's only one partnership that an AS can make. SA is also the same case, only one SA on the left, only one SA on the right. But when we come to SS, there are two SS options on the left and two SS options on the right. So what are going to be the partners? Well, we need to think a little more deeply here. If we take the example of H4 partnering with 2py, or H4 star partnering with 2s, we'll observe half of those interactions are bonding interactions, but half of those interactions are anti-bonding interactions. So overall, this is inappropriate for a bonding orbital. What does work? Well, if we look at H4 and 2s, you can see all the interactions are bonding interactions. And so this is actually the bonding orbital. Let's see how that works. So H4 pairs with 2s to produce the bonding orbital. If we take one of those partners and invert it with respect to the phase of the electron, what we achieve is going from all bonding interactions to all anti-bonding interactions, and this is the anti-bonding orbital. Next, we're going to take a look at the AS situation. With AS, we are bringing together H2 star Z with 2pz. And we do so, we get all bonding interactions, and so this is the bonding orbital. If we invert one of the partners' sense of phase of electron, all the bonding interactions transfer into anti-bonding interactions, and now we're looking at the anti-bonding orbital. Next, we're going to take a look at the SS situation. Here you can see we are partnering H4 with 2py to arrive at bonding interactions that correspond to the bonding orbital. If we take a look at the anti-bonding case, all we do is invert the sense of phase for one of the electrons in one of the partners. And what we now can see is that all the bonding interactions turn into anti-bonding interactions, and we're looking at the anti-bonding orbital now. Notice that this SS case produces bonded orbitals that have the same energy as the AS case, and also anti-bonding orbitals that have the same energy as the AS case with respect to anti-bonding orbital. They are degenerate with each other. Finally, we're going to take a look at the SA example. With SA, we are partnering H2 star X with 2px to achieve bonding interactions. You'll notice here that it's only addressing 3 of the atoms involved, namely 2 of the hydrogens and 1 of the carbons making bonds. The other 2 hydrogens aren't involved, but don't worry about this, because the hydrogens that aren't involved in the SA case are involved in the AS case and vice versa. So between the AS case and the SA case, all hydrogens are being bonded to the carbon in some way or other. Again, by inverting one of the partners' sense of phase of electron, we go from having all bonding interactions to having all anti-bonding interactions, and this is the anti-bonding orbital. You can see that this is also degenerate with respect to energy to the recently discussed SS case and also the AS case. This model is borne out by the ionization energies, and so there is a greater degree of confidence regarding this model as opposed to the hybridization model. Don't worry about the number of orbitals present here. It is a combination of all these orbitals that arrive at the overall shape for methane. And it is the same shape that is calculated in the hybridization model, and it is what we believe methane to be the shape of.